Excellent, right, and we shall kick off. So thank you very much for joining today. Today's webinar topic, I think, is really important for us to focus on because these are changes that are happening right now. And I think that's the thing, it's important to remember that this is an existing transformation. So particularly with the government's 2030-35 road to carbon zero, and that continues to develop. And really, there are three key drivers that feed into today's topic. The fact that net zero 2050 already exists, the Climate Change Committee are currently lobbying government, and combine that with COP26 taking place in November, all you've got is this big mass pushing the carbon agenda forward. Now, the electrification is obviously taking place across all sectors, so it's taken across rail, marine transport and aerospace, but today we really want to focus on the automotive sector, as that really is kind of the R&D bedrock for these type of technologies. And I think, again, it's also important to remember this is a global aspect. So it's not just the UK, but also across Europe. And the UK are really keen to lead. To that end, the catapults and other research centres are in a really good position to talk about latest technologies and really help members govern their investment strategies. So I'm very grateful to both our speakers today for their support. We've only got about an hour today, so we will barely scrape the surface, but hopefully this will start conversation and help you sort of focus on your journey and bring a few more questions to the fore. There will be a Q&A session at the end. So at that point, we will ask questions. If you've got any as we go through, there is a chat function on Teams. So if you want to pop any of those in the chat box as we go along, I will relay those to the speakers at the end. So as I've just mentioned, we have two speakers today, and I shall now introduce you to our first. So first up, we have Bhavik Saha. Bhavik is a consultant with the Technology Trends team at the Advanced Propulsion Centre, responsible for facilitating and delivering high-quality industry consensus technology and product roadmaps, as well as strategic planning for future powertrain technologies. He has extensive work experience in automotive electrification, battery production, high-volume e-machine manufacturing, value stream mapping, automotive strategy development, digital simulation methods, and has project managed several R&D funded programs. I should definitely have taken a bigger breath at the start of that sentence. So without further ado, I shall hand you over to Bhavik, who will give us our first presentation.
Thanks, James. Just sharing my screen. Could you check if you can see that, James? Yep, James, can you see that okay?
Yeah, we've got that now, thanks.
Wonderful. Thank you very much, James, for that kind introduction, and good morning, everyone. Thank you to the MTA and MTC to invite us to present these roadmaps and what we can expect going forward for electrification. So as James said, my name is Bhavik Shah. I've delivered the roadmaps last year for the APC. I was a roadmap project manager, and my colleague John Regnart, who can't be with us today, him and myself led through several workshops through industry over a 6-month program to get us to where we are. So the idea today is we wanted to share those roadmaps and the technologies coming down the road to help inform your decisions. And along the way, I'll try to pick out the places maybe where you could look at engagements and how you could get involved. So just a quick recap, the APC, APC has delivered over 150 low carbon projects since it started in 2013. We worked with just about 400 project partners on these projects, delivering CO2 savings of 260 million and more, which is growing already. And in fact, most of the vehicles which are now coming out of those projects have reached a million on-road use as well. So we've done a jobs and a safeguarding aspect of 50,000 plus as well. And that's through our competitions and our grant funded projects, as you'll probably know about as well. However, where are we going now? There's another critical pivot in the road. It's a much accelerated CO2 program, as you know, from the petrol and diesel ban that the government made for 2030, and then the PHEV aspect or the HEV aspect that comes in 2035. It's meeting that 2050 agenda for net zero. That's crucial. So we have to look at automotive transport, which is 28% of a full footprint that the UK and Europe has to think through. And the significant thing around the automotive supply chain that needs to be sorted out around the greener technologies, and electrification is where a lot of focus is being placed by government, and therefore we'd like to make sure we get that right. And one of the things that has come out of this is last year we were able to have the Advanced Propulsion Center was able to have the ATF fund, the Automotive Transformation Fund, and this is it's a brand new initiative. It is just under 400 million over 4 years to try to help progress that further as well. And of course, we need to even stretch that that funding capacity further. But this one looks at batteries, it looks at motors, power electronics, fuel cells, all the sort of technologies that are required for electrification, but primarily around capital investment. How can we make this manufacturing readiness for this is what the key focus is. So launched in 2020 June, extremely popular, and it's one of those places where we can start to look at how new technologies can be brought into the UK. What we've also done at the APC last year is launched a electrification report. This is available on our website. So what it does, it helps articulate the opportunity within the UK. Within batteries, 12 billions, within power electronics, 10 billions, and within electric machines, 2 billion. So there's 24 billions worth of opportunities. And what the report does is breaks down where those value chains reside. So where is the cathode manufacturing and anode manufacturing for batteries? How do you go about making your decisions? What about electric machines? Are you in the electric steel space, in the assembly testing phase, magnet supply? How would you like to participate? Is our invitation to read the report to understand that part of it, the value part of it. Just for this section today, we are going to focus primarily on roadmaps, and the APC delivered roadmaps with the Automotive Council. I guess, James, we've got somebody on unmute, just to confirm that, if we could get that mute function enabled, please. Okay, so Automotive Council roadmaps. The APC delivered the Automotive Council roadmaps last November at LCV, so some of you will be familiar with these. It's at the virtual event at LCV where we brought out 9 roadmaps on different ways, where 3 of them on product roadmaps, looking specifically at the kind of fleets of vehicles that we have to understand the technology migration across them. So we brought them out into different classifications. So we've got the light duty aspects, which include like commercial vehicles under 3.5 tons. We then broke out a different roadmap to look specifically at heavy goods. And we wanted to make sure the off-highway element of it was even further enhanced in our roadmap, which we've done very, very specifically with the off-highway community in particular. And then we took the bus and coach aspects and we brought out all the future trends to go with those as well. And to back that up, we build 6 technology roadmaps to service the detail around that. So that includes batteries, electrical energy storage, power electronics, electric machines, lightweighting, fuel cells. So it's a brand new roadmap of fuel cells for the first time from the APC and the Automotive Council, and then thermal propulsion systems. So although petrol and diesel is the defossilization process that we're going through, we have so much more rich technology in propulsion systems that we need to think through. That is still possible, and our roadmaps do that. So with the Automotive Council and the support from BASE, we've delivered these, so they're available. And furthermore, I'll come on to more information around these reports. So let's tackle how we built the roadmaps. So by work, although this was done over a period in 2020 with the COVID aspects, we were able to use online tools and a way to bring communities together, and running over 13 workshops across all the technologies, 109 industry companies in different organizations participating in multiple workshops. We then ran a survey, an online survey, to ask experts around these technologies, in particular, 38 of those participations, and that 147 industry organizations bringing in this rich feedback. And again, because it was digital through both Teams and with Miro, we were able to reach out a little bit further internationally to get that feedback. And so the global reach for this time round has been much bigger. And the distribution in tier 1s, tier 2s, OEMs, academia, and other trade organizations is shown there, just giving you a flavor for how we were able to get a lot of insight through this process. So let me give you an example, and then you can take the time to read it in more detail. So the product roadmaps, I'll take you through just the light duty structure to start off with, and then the heavy duty and the bus ones are there on our websites, available for download. And together with it is a report as well, which I'll share more details about in a moment. But what's different about the structure in the roadmaps that we published this year is that we wanted to look at these new ways of defossilization. We wanted to look at new ways of decarbonization, and that meant that energy and power, or how we look at propulsion is energy power, became very important. So on that bottom right-hand side, you can see a graph of power energy. It's a little bit smaller, but you can get the full copy on the website. The light duty aspects, the light green, the heavy goods area, the gray area, and the buses have a different place within energy and power. So recognizing that, we can then look at solutions on what best fits for these transport modalities. And then once we have one segmentation, we can then bring out different use case type behaviors. So here's an example of on the left hand side of how light duty, if we start to look at them in terms of use case, so urban mobility, they will need a different configuration for propulsion. Maybe battery electric will be more prevalent. When you look at long range mobility, we've got to have a mixed propulsion system where battery starts to become more difficult for charging regimes, and that fuel cells and other ICE engine technologies become more useful. And so is it, and so similarly for high power, looking at it from a high power lens, what is the duty cycle and the requirement, how that can fit in with technologies is how we broke it down. And so then what we can do is then build up a roadmap. So this is the page that then follows through on the roadmaps, where we can go through technology by technology and see its evolution on a chevron plot. And another thing that we do on these roadmaps is we bring out the energy vector. So the energy source, which is indexed at the bottom there, orange being ICE fuels, electricity or electric powered approach being green, and hydrogen on blue, and hydrogen both being fuel cell hydrogen or combustible aspects become indexed on your side here in the color codes that you can see across the bars as well. So the intention for today is just to share those give you some high level views of what products could adopt and how the journey could work along a timeline and what would work. But today's focus will be on the technologies behind these. So I'll take you through the 4 key technology roadmaps. I'll leave out the lightweighting and the TPS for today's conversation, so we can focus primarily on electrification. So let's take the first one. So it's batteries. Electrical energy storage is the roadmap. So it's a busy set of information. It's highly detailed. So the idea wouldn't be to present this to you, but share how you could possibly take advantage of it. Now, this one is this is a dual page roadmap, by the way. So electrical energy storage, we had to build 2 pages out of it. This one is the modules and pack, actually assembling the cells together and putting it in a pack and delivering those to vehicles. And there's another roadmap on cells, so cell chemistries, really looking at the cells, cathode, anode structures as well. I've decided not to bring that out today. Cells and batteries is a very different capital investment aspect and very specialist players, but on assembly processes, there's several things here that you could engage yourself with. So the simple structure is on the left-hand side, we have categories of technology within this subset, and then we've got the chevrons within it giving you detail about each one. To make it easier, I brought out the components and the skills within each one that might be of interest to you, for example. So if you're working from a different sector and you're moving into automotive, or you're moving into electrification from a traditional automotive area, or it's a startup, you can look at this map in a way that says, from cell formats and design perspective, we can park that for a moment. But from electrical energy distribution, we are going to be looking for vehicles needing connectors. So we have low voltage connectors. We'll need bus bars, sensors, software, wiring harnesses, integrated circuits. So all of these areas, if you have somewhere to play in that supply chain, this is where you would find out where the trajectories go. On the thermal management, batteries need clever thermal management systems. Again, thermal management interface materials, cooling fluids, insulation materials, all of this is again another place where you can play a role within batteries. When it comes to the mechanical systems, of which there's several within batteries, and integrating and packing them together, there is manufacturing technologies that's going to be crucial that we need in the UK to be developed. Laser welding, marking, cutting, cleaning. We need injection molding. We need aluminium housings, obviously, with different housing capability for die casting and others. Composite structures for lightweighting battery enclosures as well. And then lastly is the life cycle and end of life, which is extremely important in terms of harvesting critical materials for us. Chemical separations, looking at the second and third life solutions for batteries as well. So wherever you are within the industry, you can look at these roadmaps and start to see where you could start to play a role, and you can see the evolution of these technologies being provided on a roadmap that you just saw a moment ago there. Okay, so the next technology to move on to is electric machines. Right, similarly, a very rich area. We've broken out the roadmap so that you can synthesize that by seeing machine architectures. What's happening with machine architectures going forward? What thermal management solutions will electric machines need? And specifically for electric machines, how do I play a role within windings, magnetics, soft magnetics? So how does the winding winding technology evolve? How can permanent magnets or alternatives to permanent magnets work? Soft magnetics and looking at laminations. What's happening with steels? How can this help going forward? Or soft molded magnetics as well. And then manufacturing innovations are several parts of machinery, automation, and life cycle. So again, let's look at this from a supply chain perspective. So from an architecture and an integration perspective, you could easily look in terms of design and supplier commodities in modeling, simulation. If you've got integration services, putting things together, assembly services, bearings, axles, shafts, all of these are important for electric machines. Next is we're now operating them at very high at high speeds, generating lots of heat. Also knowing that we need to operate within a particular optimal window to get the highest efficiency out of motors, which is 93% or more, 95% quite quickly. Cooling is important. Thermal interface is important. Insulation materials, all of that aspects. If you're involved in that, you can easily participate in electric motors. When it comes to the materials area that we just mentioned a moment ago about windings, magnetics, laminations, and their manufacturing, stampings is something very transferable. Laser cutting, sheet stacking. You've got to get all the lamination stacks together, compress them together. You've got to put a shaft through the middle. There is a lot of automated winding required, whether it be different types of winding structures like distributed or hairpin. You will need precision engineering towards insertion of magnets with a glue system or a non-glue system. There's magnetization pre or post that you need to consider. And then, of course, the life cycle aspects of harvesting materials with magnet materials being important. We have a separate report on magnet materials and the opportunity on our website as well. So please feel free to reference that if you need it. Okay, and then the third one is power electronics. Now, this is a little bit more of a trickier one. This is a very specialist skill. It's not one that transfers in like we've talked to batteries and electric machines. These are specialist areas of semiconductor manufacturing packaging going forward. So it's more niche, but there are places within its cooling systems, within its materials that you could look at playing a role within. So the way we've broken this out for you at today's presentation is to say semiconductors, right, we know it's highly specialized. You'll be looking from silicon to silicon carbide. You'll be looking to go to GaN materials, gallium nitride based wide bandgap materials, but that's all about specialists within semiconductors growing these materials and the cost curves needing to come down to a particular point for these efficiency to work. But on a vehicle, where will you find these components? So you've got three places to look for these. You've got the inverter, which is bringing your DC power from your batteries into your motor. So on an inverter, several power electronics there. So I've just shown you at the bottom some of the roadmap targets that we've got around there. DC to DC, step up voltage, step down voltage. All the voltage needs to be regulated depending on the function it's going to. So DC DC on board. And then you've got the onboard charger, the charger itself that will need lots of electronics. Now, each one of these has a particular need for semiconductors, for packaging, for passives, sensors. They'll have a whole host of bits, but they also need cooling. They also need thermal management. They need insulation material. They need sensors, and then furthermore modeling, systems integration, and software development to allow these to happen. So there can be places to participate in these technologies as you go into the vehicle integration topic around power electronics. And the fourth and the last one I'm going to talk to is fuel cells. Right, this one, as I mentioned, is a brand new roadmap for Auto Council and the APC. We didn't have one before. We created a community within the UK and then reached out internationally, including Japan as well. And we built something quite robust here, including information from the DOE and from the fuel cell hydrogen community in Europe as well. Now here you'll see two color codes. Again, I understand there's a lot of information on the screen, so the idea is for you to read it at your leisure. I'll navigate you through the structure of how it operates so you can take advantage of it. The dark green colors are PEM-based software, so proton exchange membrane. These are the hydrogen-based fuel cells. And another very strong fuel cell technology is solid oxide. Solid oxide is the lighter green part of it. So they work on, solid oxide can work on several grades of fuel, low carbon fuel, blend fuels as well, whereas the PEM ones are on a hydrogen-based system. Of course, solid oxide can use a whole degree of low carbon future fuels as well. The way we've done the roadmap is to give you an idea of the technology build up, if you like, again on the left-hand side. So you can start to focus on where you want to pay attention. So fuel cell stack, is this a place where you are involved in the stack technology? And we'll come on to things within a stack that you could be involved in. Of course, there's an MEA, there's the bipolar plates, there's the gas diffusion layers, and we'll just share that in a moment. Balance of system actually means balance of plant. So it's a thermal management system. It's a very conventional areas of heat exchangers that you could look at. Power management systems, air handling and fluid systems. So that is balance of system. You've then got the fuel storage. Primarily here, we're not thinking about the tank, the conventional tank storage aspects that solid oxide can use quite quickly, but looking at hydrogen tanks for PEM fuel cells and the delivery of these with nozzles, gaseous or liquid based systems that we need to think through. And then the control systems governing this. So again, for today, we've broken this out so you can start to see although the complexity exists, how specifically you might be able to play a role in this. So I'll start on the right-hand side. So the pictures tell 1,000 words is to bring out the fact that when you look completely to your right, where you got the fuel cell as a whole, the system as a whole, you've got the stack in the middle, the red lined item. You've got the cooling systems, massive amount of balance of plant. There's a delivery systems to go with this. There is the tank itself, the hydrogen tank itself as a storage tank. So when you come on to the fuel cell stack itself, you are referring to the membrane electrode assembly, the assembly that actually brings the redox reaction together. They're made up of several membranes within it, which need particular stamping technology, which need coating technologies. You need the bipolar plates, which have a graphite coating to go with it as well. You've got to then go to other things within the hydrogen delivery system, the tank itself, the injectors, the anode outlet valves, or several valves and nozzles involved in here. Air filters, humidifiers, compressors, making up the balance of plant again. Coolers, radiators, pumps. These are the components that are typically what you're playing with. So what you can see now on the left hand side is in fuel cell stacks, stamping for the bipolar plates, chemical etching for the bipolar plates because they need to have particular channels in them, hydroforming is an alternative to the stamping, injection molding or sintering, and sintering for gas diffusion layers, which is a very key component, high value component within these MEAs. And the balance of system or plant, those will be more understood from existing technologies we have, compressors and blowers, but we need to tailor them to fuel cells. There are valves, actuators, heat exchangers, radiators, humidifiers and sensors we need through this, of which we need to find a way to design it fit for purpose, although this is a fairly well-known area of field. And then fuel cell storage. Here there are great opportunities in carbon, right? So it has to be pressurized to 300 bar or 700 bar. Carbon fiber is the forefront material for this. It's a cylindrical tank. It's filament wound. It needs carbon technology, winding technology, and valves and regulators, nozzles. All of these need to be brought together. There is a rich amount of history within the UK around carbon fiber, so we can take advantage of it. Control systems, and then the life cycle aspects that we talked about, getting these to carbon neutral and again LCA focus, which is materials harvesting and chemical separations, to get us back into a full circular value chain. So that brings me to, there's a lot of information to digest, which is why earlier this year in February we then wrote a report per each roadmap, so you can take your time reading through. There's about 25-30 pages per technology to understand the background of it, and that can give you a little bit more insight on how you'd like to play a role within this. The links at the bottom, you can go to the technology roadmaps page at the APC website or the product roadmaps page. Both have a report on it per the information I've shared with you right now. And lastly, this is the team at the APC that pulled this together. It's made up of the 4 of us. So you got the head of technology trends, which is Dave Odeniwahemi. We've got John Regnard, who helped build the roadmaps together with me, Barvik, and Luke Bates, who looks at the analysis behind some of this to make sure we get a proper data-centric approach to our information. The last thing to mention is that we're now writing up and publishing in the next few weeks, so pretty much in May, new reports called Industry Challenges. These are research and innovation topics. These are topics of the highest priority within each of the technologies I've taken you through, within batteries, within e-machines, within fuel cells. Where is the R&D needed? And we list out the high priority topics, 10 or 12 topics. And within each one, we give you research examples of the kind of places where academia, industry, and the funding is focusing at the moment. So I hope you find those useful coming forward. They will be on the website and the same page as well. Thank you for listening, and look forward to working with you. And I'll join the Q&A shortly. Thanks, James.
Barvik, thank you very much for that. That was really interesting, and as you say, a very sort of top-level overview and whiz through, but very much appreciated. We have got questions coming through, but as I say, we'll take those at the end because we'll do that for both Steve and Barvik at the same time, because we might get some bits covered in this next presentation. So we obviously talked there about some of the advanced manufacturing methods that are going to be needed. We'll touch briefly on them. So Steve is going to now tell us a little bit more on that. So whilst Steve shares his presentation, I shall introduce him. So Steve Nesbitt is the Chief Technologist at the MTC. He has 32 years of engineering experience within aerospace and automotive, ranging from continuous improvement through research and development, from manufacturing and process engineering to leading product development functions in numerous vehicle manufacturers. He also has over 10 years of expertise in hybrid and electrical propulsion systems. Steve has been responsible for leading and coordinating a number of the MTC's activities for the electrification of transport. So Steve, if I may hand over to you, I'll let you, the floor is yours.
Wonderful. Thank you very much. And thank you all for attending this morning. So the subject matter of my slides is advanced manufacturing methods for power electronics, electric machines and drives. So this is very much a subset of the full portfolio of technologies that Barvik's just taken us through. But it's with the intent of contextualizing the part that everybody could play in this. So one of the key messages I think everybody should be cognizant of in this journey is that it doesn't matter if you are a resident member of the supply chain in a current electrification sort of supply base or silo. There is a part to play because every form of product technology needs a cluster of suppliers at various tiers of the supply chain. And for each of those, there's a requirement for the provision of equipment and facilities to enable them to be manufactured. And within that, all of the tooling, fixturing, metrology systems, etc., that are necessary for a robust and repeatable manufacturing system. So it's not as though it's a closed shop and it's restricted to key actors that are already resident in automotive or electrification within automotive sectors and subsectors. There is a part to play for everybody, especially when you consider the wider sectoral requirements for the journey towards net zero technologies. So the slides that I'll go through today feature contributions from 4 key entities as listed there: the Universities of Manchester, Nottingham, University of Warwick, WMG, Catapult Centre, and the Manufacturing Technology Centre. Now, why us, we might ask? Why are we collaborating on this presentation? These 4 entities are part of the Driving the Electric Revolution Midlands Industrialisation Centre and act as a soft steering group for a cluster of a much wider fraternity of organisations featuring research and technology organisations like ourselves and key academic institutes. So we've touched upon the fact that there's a very broad sectoral requirement for power electronics, machines and drives. The same really applies to battery, fuel cells, etc., and other net zero technologies. Certain of the key targets that are listed there, the motivations, the regulatory or legislative acts that have been put in place by the UK government are promoting these. Now, we track back from some of these key deadlines, such as the electrification or decarbonisation of light commercial vehicles and passenger cars by 2035. And if you track back in terms of the delivery timescales for new product developments, new technology developments, and fundamental research ahead of that, then we're actually on the cusp of doing that now. And if we don't act soon, either the UK is going to end up or risks ending up being a net importer of technologies and therefore not in charge of its own destiny, as it were, or we lose out economically. So I think it's in our collective best interest to understand how we can all play a part in delivering these solutions to market in some way, shape or form, either within the product, the process or the manufacturing system related to it. As mentioned, we're part of a very broad national consortia of capabilities, as it were, representing 11 research and technology organizations and 23 plus and growing universities. This national network of capability is ready and at the disposal of industry to draw upon to support and enable the journey towards these net zero technologies. There's over £300 million of invested and resident equipment across these organisations that can be leveraged to best effect as needs be to support your respective journeys. These regional clusters, notionally in the Northeast, Scotland, Southwest, South Wales and the Midlands, which is actually a band that stretches from the southeast up to the northwest of England, are available for everyone to use, everyone to access. To put some context into the rationale here, here's an extract of 2 of the technology roadmaps that Barvik's already presented, and these, as noted, were recently released by the APC and the Automotive Council. The key message in both of these is and a rough translation of that is about doing more with less materials in a smaller package. So the challenges around how you integrate these systems aren't achievable solely through product innovation. Without including manufacturing innovation, equipment innovation, tooling, fixturing, etc. innovations to facilitate that, certain of these targets may not be achievable. So it's really important to understand manufacturing systems based quotient in enabling the delivery of these net zero technologies. That's why at the top right hand corner we've glibly utilize the statement manufacturing for net zero. It's about the systems base, not just solely sort of processing, as it were. The PEMD focus areas that I'll go through here. This slide illustrates the relative scale of high volume and high value economic value for the key components, subsystems, system technology groups within PEMD. The following slides will focus on a specific subset of these as listed on the left. Respecting the modest amount of time for this presentation, I shall focus on the key messages of those as I see them. First off, we'll talk about power electronics. Now, this is a very broad spectrum of major components, some of which are listed on the slide. The design of these systems is heavily influenced by the challenging electrical and environmental conditions within which they are applied. So key areas of interest are reliability and thermal management. Technologies such as double-sided cooling offers reduced thermal resistance, more power for a given die area, higher speeds and efficiencies within switching devices, and enhanced reliability and longevity. This, combined with a 20 to 30% reduction in footprint at a module level, therefore has a significant appeal. So it answers some of the key challenges around integration, doing more for less power density, and so forth. Lower materials utilization demands. Clip bonding technologies partially replaces the standard wire bond connection between die and lead by a copper bridge, which is also soldered by solder paste. So that's akin to an existing technology or processing route prevalent in electronics and power electronics industry, but offers some significant benefits. So that would be considered a minor change, perhaps, for certain of the key actors in the electronics industry now, to be able to adapt to provision of systems or components into the power electronics requirements. These things allow for unique packaging, better resistance, better thermal transfer, and ultra-fast switching performance due to their smaller package. So there's a lot to gain from such technologies. This slide covers the inactive components within an electric motor. These are the these are not part of the electromagnetic circuit, so they're mostly structural or torque transmission related components, conventionally more sort of mechanically based. These typically account for around half the mass of a motor, dependent on the type and topology, so they cannot be ignored. Many different advanced manufacturing methods exist for these structural and load-bearing components, such as radial forging and rotary forming for cylindrical or rotating parts. The utilization of non-magnetic materials or combinations of materials is commonplace in low duty cycle type applications already, such as white goods. But translating these to more arduous use cases is a developing trend. The indirect benefits of using materials which are mostly recyclable rather than mined raw materials equally cannot be underestimated. The story around magnetic materials compositions, their sourcing and abundance, and potential for impact to the environment is well documented. The focus has to be around how do we use less of these, yet still attain the same levels of performance. Some studies suggest as much as half of the material volume of magnets within an electric motor are not actually contributing to the performance of it. Manufacturing methods currently deliver regular shaped preforms, which do not lend themselves to mechanical integration or the opportunity to optimize the flux density associated with them. So near or net shape methods are needed to improve material utilization and efficiency. Clearly, the case for recovering and reusing materials is a strong one too. Many projects of work have been conducted around electrical steels and laminations, so we have a good understanding of the requirements and the impacts that discrete manufacturing stages can have on their resultant performance and/or function. But the story is not fully joined up yet. Improvements in through process modeling simulation and therefore prediction need to be symbiotic with the virtual engineering methods used for product development. The totality of these will yield far greater materials utilization in conjunction with greater opportunities for combining features to deliver additional functions. The migration towards thin and ultra-thin gauge laminations is not without its own challenges with regards to their formation, handling and stacking, components that no longer have the mechanical stiffness to support themselves. So as a for instance, typically laminations can be in the order of 0.3, 0.25 millimeters thickness. Aspirationally, we want to move to laminations that are 0.1 millimeters in thickness. That changes from being steel plate, as it were, to film, and almost taking, as an example, Baco foil thickness materials, trying to handle and manipulate those to create these lamination stacks, as illustrated in the bottom right-hand corner, present some significant challenges from a tooling, fixturing and equipment as well as processing perspective. One of the technology groups demonstrating the greatest level of innovation and development are the conductors, the active windings and associated bridges and busbars, with many different product solutions, including drawn wire, Litz wire, hairpin winding solutions, all seeking to increase the densification of windings. A good number of manufacturing process innovations are ongoing already. However, these are primarily focused on products with regular cross-sectional area, and within this present some difficulties in attaining a truly optimized conductor package. Integrating the manufacturing methods available with the intent of delivering bespoke cross-sections optimized for their respective locations within the winding package could lead to increased gravimetric and volumetric benefits, i.e. more power per unit volume or per unit mass. Elements of fundamental research are required, but the scope for near-term industrialization and scale-up for some of these are within our grasp. Integration is fairly obvious, but what do we mean by drives? Well, using Will Drury's definition from the Driving the Electric Revolution Challenge program, it is the digital controls, passive components, thermal management, and overall mechanical and system design. Embedding systems or integrating the functionality of a number of systems into a smaller number of components is in essence the approach being taken here in the physical domain. In the virtual domain, the co-simulation of multiple attributes is the next big thing. And by this I mean considering aspects such as thermal energy simultaneously with structural integrity. For example, current approach to structural optimization considers material form to achieve stress and strain requirements, but not heat transfer. Why not? There is an area of opportunity for the development of key simulation capabilities as well as the physical domain activities listed. Here is an illustration of what is possible. On the left are the high-level specifications of an industrial drive we acquired from the marketplace, in this instance a Siemens 1LE range motor. MTC have been running a number of internal short sprint style projects under the banner Future Electric Machine System. Through the three phases indicated here, we have sought to integrate form, feature and function in an increasing series of steps to yield an alternative machine with dramatically improved volumetric and gravimetric performance levels. Now, whilst the starting point was a machine designed for a specific set of attributes, cost, reliability, remanufacturability, continuous steady state use case, etc. The result is a machine which could be applied to a different set of performance and functional requirements. Regardless of the absolute starting point and current state, the relative improvements are very clear to see. We're about to publish more information about the latest iteration, PEMD 3, in the not too distant future. I've talked about a number of manufacturing process advancements in the previous slides, be they specific processes, improvements in materials utilization, or virtual engineering methods. But we cannot ignore the requirements and expectations for product utilization through life and into end-of-life activities, with the harvesting of high-value materials a significant consideration, resonating Barvik's earlier comment. Paraphrasing one of my colleagues, we are developing for all of our futures, not just today. So it's really important that we consider this factor. So, retracing my steps back to the start of this conversation, the targets are clear, albeit continuously under review. The route map to achieve them is based on doing more with less in a smaller package. In our opinion, this objective cannot be delivered by product optimization alone, and only by harnessing and the simultaneous technologies, advances within manufacturing processes and product design in unison, will we be able to get there. In conclusion, we understand the overarching goals: power density, cost effectiveness, reliability, quality assurance, and so forth. These are supported by the 4 pillars illustrated, but cannot stand on one or two of these alone. We need to consider the function we want to achieve, the features we need to deliver these, and what form represents the best physical solution. We therefore need to improve and iterate our thinking from design for manufacturing and assembly to design with manufacturing, where manufacturing refers to the materials development, creation, formation, processing, and assembly of truly integrated solutions. Should you require more details on one or more of these items, then please feel free to contact any one of us, and we would gladly help in any way we can. We are a conduit to any of the RTO or academic resources needs be if there is a particular requirement, challenge, query, concern that none of us are able to give you an expert answer for in the very near term. We can signpost you to the most appropriate authority. As mentioned, my name's Steve Nesbitt. I am a Chief Technologist at the Manufacturing Technology Centre. Thank you for listening.
Steve, thank you very much. That's much appreciated. If I can invite Barvik back again, I will just take a look at some of the questions that are coming through. We'll jump straight in. We've had quite a few come through, so if it's okay to just jump straight in. You mentioned there, obviously, about weight of batteries and weight of different components. One of the questions we've had in is about additive manufacturing in terms of lightweighting. You know, where do you see that fitting in terms of driver train, thermal management? What sort of requirements do you think will be needed for that?
Did you want me to take that, James? Is that...
Yeah, if you like kick us off, that'd be great. Thank you.
Yeah. Okay. No, thanks, James. Thanks, Nathan, for the question. Yeah, you're quite right to pick that additive manufacturing. We didn't bring that up as strongly in our themes because we had the electrification agenda, which had a few other bits of content to go with it. Now, additive has 2 aspects to play a role within. One is within, as you point out, I think in your question on the chat, is within the lightweighting aspects for sure. So one of the things we see in our lightweighting roadmap is part consolidation, taking complex geometries and making them into one. Additive is absolutely critical. And as you know, that's feasible and possible right now. What we're looking at, how can that be scaled up and how can that be scaled up economically? Well, we're seeing lots of really good progress now. Tesla themselves are using many techniques. They are even using, in terms of molding techniques, so not only additive, but they're already using other forming processes at the moment to do 70-ton machines, etc. What everyone's looking forward to now is using additive towards these. So firstly, let's get lightweighting addressed through additive, as you say, plus we can have a selection of materials under our bank that can be designed for with additive in mind that we can't get through conventional pressing processes or extrusion processes. The second place for additive in the electrification journey specifically is around the new innovation area. So there are some conventional designs that we keep getting better and better at, but we found even within e-machines, a bit like even if you look at the example Steve showed you there are some places within e-machines that additive manufacturing unlocks how windings, how stators and rotors can get together more efficiently, more packed. So do more with less, I think is what Steve said. And that's exactly what additive does for us. So we have a chance with innovation on that. And on the roadmap with e-machines, you will see additive on there. So thanks for bringing that up, and apologies if I hadn't given that a shout out. Steve, over to you.
Yeah, I resonate everything you've said. The only addition to it is designing for additive is a critical stage in developing additive manufacturing methods as a viable solution. And the rationale for that is that if you manufacture a geometry that you can manufacture using conventional means by additive methods, you're not reaping the benefits of additive. So it's very important to consider the system within it, which it will operate, and try and integrate features and content into an additively produced part. Other aspects around additive, you need to understand how you can evacuate the unfused powdered materials from additively produced parts. That's a very important factor. So you're not just carrying redundant weight for no reason if it gets entrapped within a geometry that you develop. But there are a whole raft of design tools and solutions available that can be brought to bear for that. So there's a rake full of capability around already. I could add a shameless plug for the National Centre of Additive Manufacturing, which resides at the Manufacturing Technology Centre in doing so, but forgive me.
Yeah, I think that's worth you mentioning, because I think we think that facility is really helpful for people who want to expand on the additive layer manufacturing journey. I think that's a good one, Steve. Thank you.
Cheers, thank you both. So we've got two questions now focused around sort of battery and power technology. So the first one comes in and says, a recent event of one of the major car OEMs stated that hydrogen fuel cells have no place in passenger cars. Do you share this view? So Barvik, I don't know if you go on that one.
Yeah, I'd appreciate commenting on that, because it is quite particular to product selection. Thank you. Yeah. Okay. So the short answer is hydrogen does have a role. Yes, I understand there's a lot of confusion around what's right, and this is why we're in flux. We're creating good technical basis on which we understand all of these technologies for you, Gareth, here. Right. So why does hydrogen have a place in passenger cars is what you've placed, right? We should know that the journey for hydrogen has already started for passenger cars when you look like a product like Mirai, the Hyundai Nexo, and the Honda Clarity. So that's the first. No, it's not produced in the UK, but this is a journey that started. The second one is you'll always hear hydrogen has a very strong, fuel cells have a very strong role within heavy goods industries. And you'll hear the rhetoric around that, which is heavy goods. If you try to move goods at the efficiencies at which heavy goods have been doing so for a while, on 18-hour day shifts, quite typically, utilization is high, long distance is high, time to delivery is important. The total cost of ownership is critical for these industries. And batteries at the moment, unfortunately, are unable from a mass perspective and a charging perspective to be suitable solutions, although that's work will carry on, and you'll see the Tesla semi-truck and others that will come through as time goes. But hydrogen already is starting to prove its worth there, because you've got the Hyundai Accent project. So this is in Switzerland, 1,600 prototype vehicles already in play. So hydrogen journey for trucks has begun, is started. Volvo's interested in this technology, and so is Daimler as well. Now, pass cars you bring out again. Okay, so the other thing to notice nearer to home is that in the pass car area, quite quickly we're walking into light commercial vehicles, LCVs at 3.5 tons, talking about hydrogen as a potential fuel, for the reasons of what I've just said, the convenience, the charging, and the ability for that vehicle to do more with the power density that it can do. And you also know Jaguar Land Rover are looking at one of their products to go hydrogen as well. That is a large SUV type thinking, which we're seeing in many other places as well, including the Stellantis group as well. So pass cars, if I call it 3.5 tons or lower, it's happening. The biggest market that we forecast is going to happen first is going to be in China. China is investing in hydrogen, although it's the battery leader. It realized it needs a diversified way of handling the duty cycle and the user requirements. It's already got there. It's putting more money in hydrogen than anybody else, and will be the largest passenger car market for hydrogen fuel cells in the next 10 years. So just to share that with you. And we can bring out more insights, but I think that's sufficient to give you more specificity around the hydrogen has a place within heavy goods and also in pass cars.
Yeah, I agree completely. One of the key attributes to consider with passenger cars particularly is package. And package for the hydrogen storage vessel, but also for the fuel cell itself. If the platform is not engineered bespoke to account for it, then it is very difficult to sort of retrofit into an existing platform. So it's very clear that automotive companies are looking at that as an alternative to batteries, reconciling that there are limitations probably on the supply of batteries in the future. So alternatives will be needed. Hydrogen will have a part to play, undoubtedly.
Thanks both. I mean, sticking with the battery theme, as I mentioned, so one of the next question we've had again is focusing around that in terms of temperature affecting range. So this is actually someone who has an electric vehicle as part of the webinar, who is saying they managed to do 250 miles in August in an average of sort of 20 C ambient temperature. In January, that was reduced to 80 miles at 5 degrees ambient temperature, and that's at 100% battery charge. But the manufacturer, which in this case is Mercedes, have advised that 80% maximum charge will extend battery life. So how do we all manage when we've only got a range of 60 miles? With everyone charging, the charging infrastructure will not cope with that. How do you improve battery thermal dynamics? Is the sort of next part of that question. So I don't know if you want to take that one first, Steve?
Yeah, so a specific energy density, the storage energy density of batteries, yeah, there is a huge temperature sensitivity in terms of effective state of charge, as it's known, against ambient or operating temperature for gel electrolyte systems. So one of the potential technologies to help mitigate that and counter it is solid state batteries. Now, at present, solid state is very much, let's say, in a research bridging into industrial research kind of arena. It's in the TRL, MRL 2 to 3, maybe bridging into 4 in some areas. At present, one of the constraints is manufacturing systems technology to allow scale up of volume at economic rates. So it's an understood technology. It's just not industrializable just yet, but it won't be too far off, I believe. Anything to add to that, Bhavik, on the technology perspective?
Yeah, no, it's a good question because it's a data-centric question as well. So my one comment is that it does surprise me. Sorry, yes, just to agree, temperature sensitivity exists, and that's and as Steve said, that that the industry is aware of this. Inside the batteries are separators, electrolytes. They're based on organic compounds. They are temperature dependent. Yeah. Good, and we have a problem to fix there. You're quite right. By seeing the range go from 250 to 80 does surprise me. Just giving you my personal feedback, we have several battery electric platforms now out there, other than the EQC that you have. So the Teslas, the iPaces, all of those are there. Tesla sells a lot of its vehicles in Norway. Again, Nordic regions. It has to deal with its temperature bad situation, which it has dealt with already. So the degradations they're talking about is in the range of 20 to 30% in cold temperatures, not to the extent you've said. So maybe I'll come back and say that there are some battery platforms that are better optimized around these temperature variation. It's about cell chemistry, as Steve brought out. It's about cell chemistry and understanding that. There's another little clever trick you can do is you can precondition the temperature of the batteries, and you can set that system on board as a preconditioner to give you that efficiency that you're after, that range. So it could be about an OEM strategy around conditioning. And the third thing, as has been said already, if your electrolyte and separator is the issue and you can go solid state, then of course we know from QuantumScape and others that that is a big win for that technology, which is very immature, as we know from a ready to buy situation at the moment. Okay.
Thanks both. Just a reminder to those people, I know not everyone's able to access the chat box. There is a raise hand function, so we will keep going for a little while because I think there's some good questions coming through. So if anyone wants to ask questions, you can do that. A couple more that have still come through from the chat. I think this one came through when you mentioned torque earlier on. But do you think gearboxes are still perceived as being needed in the medium term, with torque being generated by electric batteries as currently is?
Oh, not just medium term, but long term. I mean, the simple answer is that when you consider the typical torque or power curve profile for an electric motor and how that gets delivered to your tractive device, whether it's a tire or it's a rail wheel or however, there is a need for management of output torque and speed versus input torque and speed. Now, in a good many applications, there may be a single speed reduction drive so that you can make best use of the higher specific efficiency region of the motor's curve on the arc down, and match that against road speed. But you equally need to use the high torque, low speed content for launching the vehicle from rest. So it's about ratio matching. And a single speed reduction drive for passenger cars is the mainstream approach, but there are multi-speed variants coming to bear as well. And when you get into other application sectors, perhaps in aerospace, etc., where energy consumption at altitude becomes a far greater driver than thrust at takeoff and landing, then reduction drives, transmissions, gearboxes, whatever terminology, there is a big part to play still in the future. They are needed.
Agreed. Yeah. The only other angle to think at it is there is we can't shy away from the fact that gearboxes have a different role to play, and so it's single drive approach is more prevalent within electric motor battery electric vehicles. Yes, that's understood. What we are finding is that the same methods, technologies, so manufacturing gears, assembling things together, is absolutely required within EDUs. So electric drive units as integrated drive units, not motors, but you go beyond the motors and into your drive shaft. You need the gears, you need the technology. So there is in our minds a question about realizing that the industry to electrification is an opportunity for that redirection. So just to bring up that point.
The other most significant thing for the transmissions aspect is that you no longer have a nice tonal quality from the combustion engine masking the noise of gears. And so redeveloping the gear geometries and mounting of gears to make them pseudo silent, because you don't have tailpipe noises, you don't have combustion noises to cover up the high pitched tonal quality of gear meshing frequencies. Once you tune into them, they are really annoying. So they've got to be quiet as well. So they've got to be innovative as well as still needed.
Cool, thanks both. There's a few more questions that have come through. So again, I will take these in order they've come through. Given that the main competitors will be cheaper volume manufacturers, for example, from China, how do you see the UK manufacturing being able to compete other than in niche markets? So should we be focusing more on the, or less on improvements, but more on the reuse and recovery, and also ways of disposing of older technology that will inevitably be dumped?
Well, let me cite a couple of interesting points then. The UK, from a research, development and technology innovation perspective, the UK ranks, I believe, 4th in the world in electric machines, 5th in the world in power electronics. And those ahead of us are Italy, the US, Japan and Germany, depending on which product technology we talk about, not China. So there is a hotbed, genuinely speaking, a hotbed of innovation, research, knowledge being generated in the UK. So it's our collective remit to ensure that we anchor as much of that in the UK, and that we don't follow the story of original lithium-ion battery technology where it was created and invented in Oxford. We as a nation literally did nothing with it, and we lost the opportunity to the Far East in terms of exploiting that technology. So we should feel obliged to benefit from that which we create in the UK for our mutual benefit, UK economic gain. We can't compete on resource costs, labour costs with China at present, although they are rising in China. So their gains, their benefits are near to medium term, but probably not long term. As economics in China change, then labour rates will go up. So we can compete on technology near term, we can compete on technology long term. Our methods of manufacturing mean that we can be much more effective in the utilization of high value materials, and therefore we can be competitive in overall system costs rather than sort of discrete labour or direct overhead costs, as it were.
Yeah, that's really well put. I think there's just a dimension to add that is not competing against the low-cost countries with the same method as they do things, is what Steve's bringing out there, which we would like to second there. We need to do it differently. Therefore, we have roadmaps and a technology platform like these and others to make us get there, and we know how to get there. So the UK is very good at innovation, so we don't need to go at the cost. We don't have to beat the game at the same cost game. We're looking at innovation to bring the cost down. Now remember, the other aspect is about the consumer. It's a consumer's discernment about what kind of product he likes, he or she likes. Now quite often what we can do from a duty cycle perspective and a user preference, we can design products in the UK and in Europe to a better consumer demand than it can be from other countries as well, which is why we have a balanced trade approach around vehicles importing and exporting in the UK at the moment. And the second thing to notice is that we have a Nissan Leaf battery production plant in the UK that's doing really well. Of course, let's ignore last year's COVID results, but that is continuing to do well. Nissan, Jaguar Land Rover have invested in battery technology and e-machines in the UK already, so it's not that much of a moot point. These are vehicles which are sought after. We sell we will sell these, we'll export these, and we'll use them internally within the UK. The Mini itself is going to be electrified. It's going to be in the UK. So there is still a rich opportunity in the UK to keep our innovation towards these new technologies. So I hope that's possible. And just echoing, the other thing that we don't realize is the e-machines industry has been an absolute bedrock within the UK for many years in small niches. Yes. So we recognize we have got pockets of intelligence all the way through the country. We're talking about south of England, all the way to Newcastle and further on, that these pockets exist. We've known this for a while at SME level, at tier 1 levels. This is the chance for them to grow into those players that wasn't there as a demand requirement before. So we are rich, and being third and fourth in the world is exactly the point we're trying to bring out. Thanks.
According to ONS data, in the UK, year before last year's data is not complete yet. Year before last, we produced between electric motors of all kinds, industrial drives, generators, electrical pumps, and transformers, 17 million units. Now, they're not utilised. A large proportion of those are not currently applied to transportation-related applications. But there's no reason why the know-how, the manufacturing capability, footprint, etc., can't migrate over to support those sectors as well.
Sure, thank you. We focused today obviously a lot on some of the newer technologies, and there's a lot within electric vehicles and electrification that we've looked at. But where do you both see existing manufacturing technologies in the not too distant future? So do you think there'll be a decline in sort of subtractive and material removal as we move towards composites and additive manufacturing? Or do you think there is more place for subtractive?
Very simple answer, yes, there is, undoubtedly. And the reason for suggesting that is that producing net shapes or donor shaped materials, economically at the moment, it's still mostly more viable to do it via traditional methods than additive. One of the reasons Babik rightly hit upon is about the throughput rates, the production rates through additive. Now, there are very large machines available now in the marketplace with sort of 2 and 3 meter wide beds with multiple laser sources for powder bed fusion manufacture of metal components, and so the number of components it can create in a build is into the thousands. Depending on obviously the relative size of the component in question. So the scale-up rates of additive are coming. They're not there for every form of component or material type yet. So there's a broadening spectrum of materials also within the additive arena that are still being developed. There's lots of aluminium alloys, there's steels, there's tungstens, there's aerospace materials, etc. There is a huge portfolio of materials that you can produce additively, and that's just the ferrous. There's also ceramics and polymers, and even composites can be produced by additive methods. So they are getting there, and they're on the cusp of that curve for ramping up to get towards really high volume mainstream production for additive based parts. Subtractive will clearly play a part. Until then, depending on the specific geometric needs of the component, you may actually still need a form of subtractive manufacturing with an additively produced part. Really depends on the topology, surface finish, surface roughness aspects at a microgeometry detail. So yes, there's still a need.
Yeah, so yeah, just a few comments from my side. No, additive layer is not going to take over all manufacturing, and composites is not going to take over all manufacturing. I think has been echoed. It'll be part of the growth of the next generation of vehicles that we're looking forward to, as Steve just said. So the traditional. So let's break this down into traditional materials. Yes, we have a very rich steel demand still. So you'll see on the lightweighting roadmap, you'll see that steel. And you also see aluminium. And one of the things that we're seeing is aluminium is growing by a large amount, and recycled aluminium has a big role to play within it. So materials-wise, steel and aluminium big. We did a survey. We found out actually all of the platforms 2030, 40 will be relying heavily on aluminiums for its unique capability, extrusions, and getting some of the forming shapes. We'll be relying on steels for what it's good at. We need some composites in some places. So we weren't talking about full transition to composites here. We're talking about how these materials are going to come in and play their role, and additive is going to replace a few parts of complexity, but we'll never do the sheet metal. It'll waste your time doing that, right? Then the next way to think about this is traditional technologies, right? So what we got the body in white. We've got all sorts of new things coming in. That still is going to be traditional technology aspects. We're replacing a fuel tank. Yes, but that's a low value aspect replaced by something high value called a hydrogen tank or a battery storage system. So what we're saying is we're getting high value added into these cars. So we're going from a £30,000 car to a £50,000 car. What we're saying is there's some new value here. So we're not saying displacement here, we're saying new value. The ICE engine is changing either to new ICE, but also not having an ICE and having an electric motor. Here's some new value that we've created in that process, and that's happening. However, there's some skills within ICE that we still will be needing. We'll need the machine operations, we'll need the casings, we'll need things to do with gears as well. We need all of that. And so repurposing that will be important. Yes, we're not going to be combusting and igniting gasoline and diesel. I get all of those injection technologies, and all of those will have a difference to go with it. But what we have now is a richer new set of aspects to look forward to investing in the UK for. So all technologies are definitely required. Some will need a little bit of transformation, which are the ones I've said. And then there's a next stage, which is look out for these new opportunities for electrification and UK strengths, because we need to build it together as a community on these opportunities that Steve and I have presented today. Okay. There is one angle that I maybe want to bring up, James, at this point, is that industry should think about two key things which are slightly different, and it's something that Steve and I have both shared, but maybe need to land this. One is energy, and the second is circular economy. So I know we've tried to bring this out, but remember what we're talking about here, chaps, in industry, is we are dealing with something of a crisis at the moment with it, which has caused the electrification to come through, and that crisis obviously has got the name climate change crisis. Energy and how we use energy, where we get our energy, renewable energy, to make our plants function or our cars function, is just as important as what we're talking about right now as technologies. So even how you manufacture or how your total supply chain works is important. And that could mean why we store hydrogen from renewable sources becomes a strategy for the government, for example. And the second thing to know is every material is going to have value. So everything we scrap needs to be looked at properly to say that needs to be circular, back to circular value chain. So every battery will need to be recycled back into its ingredients, as we know, which is the topic of interest. But aluminium already getting there, steel's trying to get there. We need to keep that focus going, and our roadmaps will explain we need to get that right.
Yeah,
Okay.
just to add on the energy point, on notionally on any given day, the UK has the ability to generate all of the energy it needs, electrical energy it needs, in a 24-hour period. The issues with the transmission system and distribution grids is capacity at peak times. So there is a need for technologies to augment with some form of energy storage and buffering arrangement, so that we can promote a sense of energy security within the nation. And part of it is our migration towards green and renewable energy sources, as opposed to fossil fueled generation methods, and they all play part of a big ecosystem. So, you know, things like electric vehicle smart charging systems, DNOs like EDF are already offering specific tariffs to domestic EV users, so that you commit to charge your EV overnight at low power demand times rather than at peak times. And they will offer you a premium on electricity tariff in your house as a result. So, you know, these things are coming.
Yeah, thanks both. And you touched there again on circular economy. I know Circular Economy Week is coming up in June, and we are putting a few bits together. But I know that I think the APC are doing something around battery technology, if I'm right in saying so.
Yeah.
As part of that. So again, we'll get details out to people. I've had no more questions come through on the chat. No one has their hand raised, but again, I know people sometimes have issues. So if anyone's got any questions whereby they want to unmute and shout their name out, as it were, then we can always go over to you. We'll give that a second or two just in case there is anyone. Otherwise, as I mentioned at the top, both presentations will be available afterwards. What we'll do is we'll get that circulated to everyone that registered for the event, along with the recording from today. And we will also send out a short, just 2-minute survey, just in terms of feedback form for this, to see if there's any other topics you want us to cover within this area, or any other areas. So it seems like that is all we have. I'm just going to check one last time on the chat. Nope, that seems empty. So in which case, I will say a very big thank you to everyone to attending, and a massive thank you to Avik and Steve for the 2 presentations today. And again, both your contact details I noted on the end of your presentation. So yep. I'm sure if there's any follow-up questions, you can either do that directly or by all means come through myself or the MTA. So many thanks to everyone for attending, and enjoy the rest of your Thursday.
Okay. Brilliant. Thank you all.
Thanks so much. Cheers all.
Take care. Bye-bye.
Thank you. Bye.
Cheers.